3-Eye Atlas is getting more company as it heads toward Earth. Astronomers tracking the twin anomalies, Swan and Atlas, were already straining against the limits of observation. Both had entered the solar blackout window, disappearing into the sun's glare at the very moment of closest approach. It should have been a pause in the story. Instead, it became the escalation. Because on the edge of that blackout, instruments registered a third visitor. Brighter than Venus, moving faster than any comet on record, and emerging from a sector of the sky no models had predicted. Its apparent size already rivals the great comets of the last century, despite being only days from discovery. In less than a season, the inner solar system has received not one, not two, but now 3 anomalous inbound objects. The odds of such a sequence occurring by chance are vanishingly small. Even cautious voices within the International Astronomical Union admit there is no recent precedent for it. The official designations call them comets. But the geometry, the timing, and the sheer improbability point to something stranger. Swan with its fortress-like halo, Atlas with its stepwise accelerations, and now a third object appearing in synchrony with both. Why should we care? Because this convergence unfolds while Earth's telescopes are blinded, leaving only fragments of data to decide whether we are witnessing nature at its rarest or a coordinated mission passing just beyond our reach. What happens when the sun itself becomes the stage for a rendezvous we were never meant to see? The first alert came not from Earth, but from deep space. On October 19th, the Parker Solar Probe's Wide Field Imager for Solar Probe, or WISPR, flagged a bright intruder crossing its field. Hours later, ESA's Solar Orbiter Coronagraph confirmed the detection. A new inbound object, unmistakably luminous, had appeared at the inner edge of the solar blackout. Initial photometry put its brightness at magnitude 3, rivaling Venus. Even through the solar haze, its core registered sharper and more compact than most comet nuclei. Preliminary motion estimates suggested a steeply inclined trajectory, not aligned with either Swan or Atlas, but arriving at nearly the same perihelion corridor. The contrast with earlier discoveries was striking. Atlas had been found months earlier by wide-field sky surveys, faint at first and only later showing anomalous pulses. Swan erupted onto the scene in September, blazing so brightly its tail stretched 5 times the width of the full moon. Both were discovered in ways consistent with standard comet tracking. Ground telescopes first, satellites later. This third object reversed the pattern. Hidden until the final days, it revealed itself only within solar instruments, not to the global network of ground-based observers. And unlike its predecessors, it was already too bright to ignore. The timing could hardly be more pointed. As Swan and Atlas disappeared into conjunction when no Earth-based telescope could watch them, a third body entered the same corridor. Whether natural coincidence or a coordinated sequence, the effect was the same. Astronomers found themselves watching the start of another anomaly with no way to see it directly. To understand why the appearance of a third object is so unsettling, consider the normal distribution of cometary arrivals. The International Astronomical Union's Minor Planet Center maintains thousands of comet records spanning centuries. The overwhelming majority appear sporadically, often separated by months or years, with perihelia scattered across the calendar. Long-period comets, those returning after thousands of years, are rarer still, sometimes arriving only once in several generations. Statistically, the inner solar system might expect 1 or 2 bright, naked-eye comets per decade. The clustering of 3 within the same quarter of a single year is beyond precedent. Astronomers accustomed to randomness are instead forced to confront synchrony. The geometry deepens the puzzle. Atlas entered from the direction of Sagittarius, Swan from Aquarius, and the third object from a still different sector near Scorpius. On a star map, these vectors span more than a third of the celestial sphere, yet all 3 are now converging on solar perihelia within a span of less than 3 weeks. Their perihelion distances are equally curious. Atlas skims at roughly 0.2 astronomical units, Swan closer to 1 AU, and the newcomer somewhere in between. To have 3 large bright objects intersect the inner solar system with such close timing from such different inclinations is the kind of scenario orbital dynamicists usually encounter only in simulations. By chance alone, the probability of 3 unrelated bodies choosing the same corridor at the same moment is vanishingly small. The question then is whether nature has conspired in improbable fashion, or whether another organizing principle is at work. The blackout window is a familiar frustration to professional and amateur astronomers alike. Each year, as Earth moves behind the sun relative to a given object, observations are interrupted. For comets nearing perihelion, the glare of the sun overwhelms even the most powerful ground-based telescopes. In October 2025, that window falls between the 8th and the 18th. For Swan and Atlas, this meant their most critical days, their closest approach to the sun, were hidden. By the time they re-emerge into darker skies, whatever activity occurred during peak heating will already be over. But this year, the blackout carried an additional surprise. The third object entered the corridor precisely as the other two disappeared, creating a sequence of arrivals no ground observer could follow. Solar Orbiter and Parker provide partial coverage, but their instruments are not designed for full-scale cometary analysis. High-resolution spectroscopy, radar imaging, and coordinated photometry, all the tools that normally reveal a comet's true nature, are effectively shut down. The geometry compounds the challenge. All three objects are on steeply inclined orbits, their approach angles so different that no single vantage point can capture them together. Yet from Earth, the alignment collapses into a shared absence. The very moment the solar system delivers its most improbable trio, our planet's telescopes are blinded. This is more than inconvenience. It creates a corridor of invisibility, a blind spot in which critical data vanish. Whether by accident or by design, the blackout has become the stage for convergence. The solar system is hosting an event of staggering rarity, and Earth can only watch from behind the curtain. Long before the third object appeared, Atlas had already unsettled observers. Early spectra taken in July revealed a composition few could explain. Instead of the standard iron-nickel blend seen in comet vapor, Atlas showed nickel almost entirely without iron. Laboratory teams called for calibration checks, yet repeat measurements confirmed the anomaly. Then came the gas profile. Most comets release water vapor as they near the sun. Atlas did not. Instead, its coma was dominated by carbon dioxide, emitting at rates 5 times higher than water. Rare, but not unprecedented. What could not be so easily dismissed was the rhythm. Observers logged 3 distinct accelerations, sharp boosts in velocity spaced roughly 2 weeks apart. Each surge coincided with a shift in tail color and a sudden jump in brightness. Natural outgassing tends to be gradual. Atlas moved as if something inside had fired a controlled burst. By late September, additional reports confirmed the pattern had not stopped. Amateur networks in Chile and the Canary Islands tracked a fourth modulation in tail direction. The cycle remained consistent, as though Atlas was following a timetable. Energy estimates raise further questions. If the accelerations are genuine, the implied output reaches nearly 10 gigawatts, the scale of 10 nuclear plants, far beyond what a fragment of ice and dust should produce. The official stance is cautious, stressing unknown surface processes and the risk of systematic error. Yet the anomalies line up: nickel without iron, CO2 dominance, and stepwise thrusts. Taken together, the evidence keeps alive the hypothesis that Atlas is not behaving like a natural comet at all. If Atlas acts like a drone, agile and unpredictable, Swan has taken on the role of a fortress. From the moment of its discovery in September, its scale defied precedent. A tail stretching more than 2.5 degrees across the sky, 5 times the width of the full moon. A brightness peak that rivaled Hale-Bopp and other giants of the last century, and a calculated orbital period of 22,554 years, so long it stretches back to the last ice age. The anomalies have only deepened. Reflectance spectra suggest a core unlike ordinary ice and dust. Instead of the diffuse scatter typical of comet nuclei, Swan's nucleus shows sharp returns, hinting at a dense metallic surface. Some observers see signatures of a nickel-cobalt alloy, materials prized on Earth for strength and corrosion resistance. The phrase nickel-cobalt hull has circulated across forums, though it remains speculative. Amateur astronomers add to the mystery. From Spain, Japan, and South Africa come repeated reports of a silvery halo surrounding the core. Not a faint glow, but a persistent, shifting envelope that resists the solar wind. Some describe it as a plasma shield, a kind of electromagnetic sheath. Energy calculations reach staggering levels. Swan may be radiating power on the order of 10,000 gigawatts, 1,000 times greater than Atlas and more than the entire human power grid. No known natural mechanism scales to that level without catastrophic disintegration, yet Swan holds together. Whether coincidence or choreography, Swan is not simply another comet. It is luminous, shielded, and seemingly invulnerable. A long-period fortress sweeping into the solar corridor after 22 millennia of absence. With Swan and Atlas drawing scrutiny, the third object arrives almost as a cipher. Detected only days before the blackout, its profile remains sparse, yet the few readings available raise new puzzles. Coronagraph spectra from both Parker and Solar Orbiter show no trace of the usual cometary gases. No water signature, no carbon dioxide line. Instead, a narrow but strong emission appears at 585 nanometers, the wavelength of neutral neon. Neon emission is common in laboratory plasmas, but no known comet nucleus produces it as a dominant feature. Brightness analysis adds another anomaly. Photometric data reveal a repeating pulse every 9.8 hours. The light curve rises and falls in precise rhythm, as if the object is rotating with a beacon-like flare. Astronomers call it a thermal heartbeat, a cycle difficult to reconcile with chaotic outgassing. No size estimate has yet been published, but if the brightness holds, the core could rival Swan's in scale. Its inclination is steep, its perihelion close, and its timing uncanny. Entering the corridor exactly as the others vanish into blackout. Speculation is inevitable, but must be labeled as such. One hypothesis is that the neon line reflects an exotic mineral surface, perhaps exposed by a recent fracture. Another, less conventional, is that the emission is engineered, an intentional plasma discharge or signal. Both remain unproven. What is clear is that this third object is neither faint nor ordinary. It arrived hidden until the last possible moment. It pulses like a machine, and it carries a spectrum that belongs more to a laboratory arc lamp than to an icy body from deep space. With 3 anomalies now converging, astronomers are left with more than data. They are left with choices about interpretation. The official narrative holds to chance alignment. Rare, but possible. Yet the geometry and timing invite alternative frameworks, always marked as hypothesis. The first scenario is the solar pit stop. In this view, Swan, Atlas, and the third object are engineered probes, using the sun as a power node. Solar flybys are a standard tool in human spaceflight for gravity assists and energy boosts. If scaled to interstellar missions, perihelion could serve as a recharge or data relay point. The second framework is the audit chain. Oumuamua in 2017, Borisov in 2019, Atlas in 2025, Swan, and now this third intruder, each arrival more luminous, more complex. In this interpretation, every new visitor represents an escalation, as if the solar system is being surveyed in successive layers of detail. The third is the rendezvous mission. 3 objects, arriving from widely separated origins yet meeting in the same corridor, may not be coincidental. Their synchronized perihelia suggest choreography, a convergence that could allow data handoff or mutual calibration. Mainstream astronomers caution against overreach. They stress the risks of calibration drift, the small number statistics of comet clustering, and the temptation to impose patterns where none exist. Still, the vanishing odds, the accelerations, and the spectral oddities leave the hypothesis of a mission difficult to dismiss. If the anomalies raise questions, the flow of information raises more. As Swan and Atlas slipped into conjunction, both U.S. Space Command and the European Space Agency circulated internal directives. Teams were instructed to suspend high-resolution imaging during the blackout. Radar allocation requests were denied. Even routine photometry releases were delayed or rerouted. On paper, the rationale was safety, protecting instruments from stray solar glare. Off the record, reviewers described blanket restrictions, far stricter than usual. One telescope manager called it a hard stop. The effect was silence, imposed at the exact moment when anomalies were peaking. In contrast, grassroots astronomers have been anything but quiet. The Ibero Collective in Spain pooled wide-field camera feeds. Independent observers in Australia and Chile attempted makeshift radio monitoring, listening for sideband signals and frequencies normally used for spacecraft tracking. Bill Gray's open-source orbit network pushed out daily predictions, urging backyard astronomers to keep logging coordinates even without direct visuals. This divergence is striking. Institutions with the most powerful tools have fallen silent. Amateurs with modest instruments continue to post data, share plots, and circulate images through public channels. Some argue that the silence itself has become a signal, a kind of indirect confirmation that what is unfolding is not routine. For those outside professional networks, the blackout does not mean the story ends. When Swan, Atlas, and the third object re-emerge from the solar glare, they will be faint but trackable. A modest telescope, or even binoculars under dark skies may be enough to catch Swan's fading tail. Photometry apps allow backyard observers to record brightness shifts. Radio enthusiasts can listen for anomalies in sideband frequencies where subtle drifts might hint at non-natural modulation. The recap is stark. Atlas, with its nickel signature, CO2 dominance, and stepwise accelerations. Swan, luminous beyond precedent, armored in what some describe as a nickel-cobalt hull, radiating power at scales greater than Earth's grid. And now a third object, hidden until the blackout, pulsing with a thermal heartbeat and emitting neon light. 3 anomalies, 3 different signatures converging in the same solar corridor. Whether natural coincidence or engineered choreography, this alignment will not repeat in living memory. The orbital periods stretch into tens of thousands of years. The next chance to witness such a convergence lies beyond the reach of human civilization. The stakes extend beyond astronomy. This is about epistemic truth. Whether the solar system delivers chance events beyond probability, or whether the cosmos is operating on principles we do not yet grasp. When the blackout lifts, the first data may not come from agencies or classified instruments. It may come from you, from the backyard telescope, the shared spreadsheet, the unfiltered feed. The sky has delivered 3 anomalies. The question is what we choose to see in them.